Thanks again. I'm excited to be here. Thank you for the nice introduction, Alex. So as some quick motivation, there's been a lot of motivation before me. I'm very thankful to go late. But the ice sheets are rapidly losing mass. And in particular, when we look at Greenland, projections have it losing or contributing up to 1 meter to global sea level rise by the end of the century. And up to half of this could be through calving processes at the outer margins of the ice sheet. An important process that could potentially moderate this process is the presence of a thick ice melange, which is this little bit right here. I know I need to find a better photo, but we've made it here so far. This ice melange, if you're not familiar with it, is a dense mixture of icebergs, sea ice, brash ice, that forms this dense particle, granular fluid that flows in very difficult to model ways, but can provide significant backstress to the glacier that can control calving. And then, not to be confused with the dense sea ice that's out in front over in the ocean within this fjord and the glacier in the background here. And these glacial fjords are currently choked with melange, most commonly found in Greenland, but there are also places in Antarctica that have similar processes ongoing. And so to give a little more motivation for this feedback between calving and melange, these are some very nice observations in a paper earlier this year by Olivia Mang, where we see the terminus position of Helheim Glacier in the black dots, and the melange thickness just in front of that terminus in blue, and calving events highlighted in red. And we can see that periods of thicker ice melange providing more buttressing stress correspond with regions of, or times of paused calving, and times of intense calving correlate with regions or time periods where there is a thinner melange, allowing for that accelerated calving. And then, as we also heard about earlier today, there's important feedbacks between the melange and the icebergs within them and the ocean, where the melt of these icebergs can be a significant contributor to the freshwater budget of these fjords, which then contributes to freshwater into the ocean beyond. And so this motivated our project to look at the individual components and then also modeling all three of them together, the glacier, the melange, and the ocean itself. This is part of a much larger collaboration, and I'm excited to be the one that gets to tie it all together. So here's a diagram on the right that you can follow as I move along. But one of the key questions that I've been thinking about is how the glacier feeds back with the melange. And this sort of hypothetical question of, can accelerated calving of glaciers, will that lead to a thicker melange? And can that melange provide enough buttressing stress to slow the calving of these glaciers and slow down the collapse? But other processes we need to include here as well is that the melange interacts heavily with the ocean by injecting meltwater and also being a barrier to ocean flow. So there's slower currents within the melange itself. But the ocean can very quickly melt the melange, which could mean that if we see warmer ocean forcing, and that reduces melange, maybe glaciers that are currently restrained, their calving is currently restrained by melange, maybe that melange will disappear and there will be accelerated calving in the future. And then the final connection is a connection between the ocean and the glacier, and that's largely through effects like Becca talked about yesterday. And so to start zooming in on this coupled system, we'll start with our melange model. The melange model is work that was done by Jason Amundsen, published in the Cryosphere earlier this year. I'll go light on the details in respect to time, but he has a continuum model for ice melange. It's a 1D depth integrated model. The important part here is that it solves for melange properties like depth, extent down fjord, buttressing stress, and it solves for those as a function of the ocean forcing the melt from below, as well as glacier forcing, like the calving rate supplying mass to the melange. And so the first question that I really dug into is how we can realize this very smooth melange that we get out of our melange model. It gives a very smooth melange draft profile that's thick near the glacier, thin by the toe. But when we look at actual observations of melange, this is a satellite photo of Helheim again, it's very rough. There's lots of very, very large bergs. There's, or small number of very large bergs, many more, a few really big bergs, lots of really small bergs, a power law, and that we need to incorporate that effect into our ocean model because the overall surface area of this rough melange is important for getting the correct surface area for melt. And also these deepest bergs penetrate very deep into really warm waters in these fjords, and that's going to make a really big influence on their average melt rate. And so to do this, this is part of the reason why we selected MIT GCM as our ocean model. There was an existing iceberg package, which was called Iceberg. I now call the extension Iceberg 2. Within MIT GCM, that was developed by Ben Davison. And this allows for the realization of subgrid icebergs. So within every grid cell, this is an MIT GCM grid cell, you can have an arbitrary number of subgrid icebergs that each have their own dimensions. They're all rectangles, but they have their own height, widths, and lengths. And we can solve for melt at every depth slice on every face of each of those glaciers, sum together the melt contributions, pass those heat and salt tendencies to MIT GCM for the next time step. The extension that I worked on was to allow for the inclusion of drag effects, because the ocean flowing through these really dense melanges that have up to 90% ice, there's a significant reduction in ocean flow because of that ice presence. And so that is done by parameterizing the bulk effect of blocking and drag, again, at every cell and at every level. So we can more accurately capture the flow rates in the ocean, which are very important for setting accurate melt rates. And if you're curious about this, the Iceberg 2 package is available on Zenodo, and you can leave a nice comment or a mean comment, it's up to you, on the preprint in the cryosphere, and I'd be more than happy to write a response. So then what this step actually looks like within the coupled scheme is from our Mélange model, we get a volume profile and an advection speed. We then pass it to a script that turns that volume profile into discrete icebergs that are drawn from a power law. That power law is based on observations of iceberg sizes in fjords in Greenland, and also advects the iceberg size as they move down fjord and melts them at the rate that they've been melted in the ocean model. The ocean model then runs for a full day with about 10-second time steps, and then we pass the Mélange melt rates back to our Mélange model, take the next step forward. And then for going back to our three-way diagram here, the coupling between the ocean and the glacier, we use buoyant plume theory using a package, Ice Plume, by Coughton in 2015, which Becca talked about yesterday. So again, won't go too much into the details here, but it is in our ocean model. And then the final link is our link between Mélange and the glacier. Future work will include a more sophisticated glacier model, but for now we're sticking with a very simple linearized calving law, where there is the calving rate that is feeding the Mélange, U sub C, is set by some background calving rate that for these experiments will keep constant, and then a linear term that says the more buttressing the Mélange is providing, the calving rate will be decreased linearly. And we choose an arbitrary alpha value here of 25 times 10 to the negative fifth. This is pretty early work. It's kind of an arbitrary guess. It seems to be a relatively small forcing, and the results will show how our results vary as we adjust that parameter. But this is just to see, with a simple linear relationship between calving and buttressing stress, can we get seasonal behavior that reflects what we actually see in fjords today in Greenland? And so to give you a quick run through of what the demo will look like, or our initial model results are, we're in a 92-kilometer long fjord. It's just over 5 kilometers wide, 600 meters deep. The glacier is on the left. The Mélange is about 20 kilometers long to start, and there's a 400-meter line plume in the center of the glacier on the western side. On the eastern side, we have shelf conditions that are temporally constant, but do vary in depth and are based on observations of Sørmark Fjord in the summertime. For scale, for those that are keeping track, this isn't super high resolution, but it's not super low resolution. It's about 400 meters, and it has 32 vertical layers. And for our seasonal forcing, we only have one seasonal driver, which is we will be varying the subglacial discharge. The winter values are about 10 cubic meters per second. That's a 240-day long winter. Then there's a 120-day long summer, where we ramp up a subglacial discharge from that winter values up to 1,300 cubic meters per second in this sinusoidal ramp. And that'll be the only forcing. We run this for a few years, but I'm going to run you through the second summer, so days 440 through 805. I'm very pleased that I think you can actually make out these quiver arrows. I think I made them just big enough. But there's two slices here. So the top view is a map view. Thank you. A map view of the fjord. The dashed line is the walls. You have some non-ocean cells on the boundaries. The Mélange, again, is on the far left. The melange is labeled now, but will just be the gray shading when we're actually running through the videos. And this is a slice at 50 meters depth and shows ocean velocities, where the darkest greens are 20 centimeters per second, so pretty rapid flow. And then down below, this is ocean temperature. This is a slice straight down the center of the fjord. So the discharge plume is within this profile. And we can see that the vertical axis is now depth. And this is the temperature field. We can see the warm, deep water. And this snapshot is January 1st. So we can see that it's mostly in the wintertime-like condition where you have very cold surface waters. The melange is quite extended. And again, the melange is shaded in gray. We can see here the rough, long tail of the melange, where these shading cells have at least one iceberg within that cell. So they are mostly ocean, but there is some ice extending down to that depth, whereas higher up, it's almost entirely ice with a pretty smooth gradient. But that explains why the shading goes so far down. And to sort of highlight why it's important to have these rough extensions, and you can see how it's very warm and a lot of melting is happening in those regions. And then finally, to keep track of time, this is the timeline sweeping through the summer. Yellow is the summer, and the blue line is that subglacial discharge. It's easier to watch if it's over there, so I gave you a little small one, and I'll let this run. And so we can see in the ocean a pretty distinct transition from summer to wintertime conditions, and we see the melange moving back and retreating during this time as well. There's a lot of neat things that I'd love to dig into more with this, but alas, I only have so much time, and so I'll keep going. But to focus on the seasonal response of the melange itself, here's a plot of the melt rates in red. They're smoothed for a 10-day average, as well as the calving rates in blue. And so we see here that there's intense melting in the summer, and that the calving rates accelerate through the summer. Although we're not solving for the terminus position, this accelerated calving rate you could see as a proxy for glacier retreat throughout the summer. This acceleration of the calving rate comes directly from our drop in buttressing stress in our melange, because we made that the case in our calving parameterization. And this buttressing stress is coming from the decreasing in size of the melange as it melts rapidly in the summer. But importantly, a feedback I want to point out is that the increased calving rate at the end of the summer leads to an earlier initialization of growth again at the autumn, because there's so much more calving, there's more mass flowing into the melange, and it starts this building period just before the end of the summer. And that's more clear when we consider a coupling parameter that's 4 times as strong. We see that the melange begins its build just a little bit earlier in the summer, owing to a much higher calving rate at the end of that summer. And we also see that the melange on the whole is sort of a more moderate size. It doesn't grow as big in the winter. It doesn't shrink to be as small as we increase this coupling between the calving rate and the melange buttressing stress. 1 minute left. Oh, I actually finished kind of on time. Sorry for rushing. So I get to talk about my future directions now. There's lots of work that continues to be done that I'm very excited to continue to work on or collaborate with others. I think at every individual model component, there is more work to be done. We could use an actual glacier model, either a more sophisticated box model, or a big flow line, or 2-dimensional, 3-dimensional ice sheet models. There's ongoing work at Georgia Tech that's developing a 2D version of the melange model that will allow us to actually resolve realistic geometries of fjords. And that'll be done in fire drake, so it would actually pair quite nicely with something like ice pack. But we're still pretty agnostic to whichever glacier model we want. And then finally, in the ocean model, we heard a lot about how iceberg and iceberg drift and melt is very important. Right now, we're not resolving icebergs beyond the end of the melange, but we're working on ways of being able to include those Lagrangian icebergs that drift through the fjord and contribute to freshwater flux at depth to better resolve freshwater export estimates for fjords across Greenland. And with that, I'd be happy to take any questions.
All right. Thanks, Paul, for the wonderful talk. Questions?
Yeah, thanks for a cool talk. So I'm curious, can you describe more how, in the model, how do you specify the interaction between subglacial discharge and the melting of the melange, because that causes seasonal variation?
Yeah, so the melt rates are all handled within the ocean model. So the ice plume package takes the subglacial discharge and solves for its neutral buoyancy height, and sort of exports all of that plume water entrained with water from depth. And then that goes straight into the ocean model to drive this like forced flow through the melange of this warm, salty water. And then that's where the iceberg package calculates discrete melt at every face of every iceberg. And the melange is often composed of like tens of thousands of icebergs. So we're resolving melt on all of those faces, and then we get the net freshwater export and convert that to a melt rate for the melange model to take up.
Yeah, super fascinating. Thank you. I was just wondering whether you have enough cross-channel resolution to see whether there's a cross-channel variance in your flow, like because you have that plume in the center, right? And so I think sometimes you can see like a jet coming out in the center of the fjord, and then maybe some recirculation. I don't know whether you saw any signals of that. Whether you looked at that.
Yeah. Yes, we did a lot of work on this in actually implementing the iceberg drag for the preprint we have out now. And without the presence of iceberg drag, you do see these very strong jet effects. But once the melange is present and has drag, it really averages that out. And so we see, without iceberg drag, there is a lot of cross-fjord variability that we do capture. We have like 24 cells that go across the fjord. But once we put the melange back in, even though we could resolve if there was an asymmetry, but we see that it's very homogeneous within the melange. And then once it's outside the melange, we see some asymmetries. But the plume signature and the jet, we don't see quite as much.
Very cool. Thank you.
Really fascinating work here. I have a question about the sea ice package in MITGCM. Do you have it turned on in these simulations? And if so, how does it interact with your melange parameterization?
Unfortunately, we don't have it turned on yet. I think that's more future work that we could have in the ocean model. I think it's important to include, but currently not within the model. So yeah, this seasonal cycle had no sea ice, which definitely plays a role in helping the melange stabilize itself through the winter months, but is not included in the model so far.
Paul, I have a question for you. I promise I won't ask you a question that I already know the answer to. A few people have mentioned for Antarctica the possibility that melange or a melange-like thing could be playing a role within rifts. What do you see as the prospects for implementing a model like this for rift melange?
Yeah, I think in the rift geometry, having a 2D melange model will be more important because it feels to me like a more 2D flow field. So I think with some of Ziad's work, that'll be a great extension. I think the framework that I've developed here could certainly extend to that. I think the intuition won't scale in the same way. Because I think here we have a lot of warm water that's being sort of flushed up into the melange. In the rift zone, you have thick ice shelves on both sides. There's probably lots of other ambient melt that's coming in and filling. So I think the model approach could be very similar, but I'd be really interested to see what the results might look like.
I'm curious, is there some width of the fjord at which the backstress applied would no longer be enough to prevent the outflow of the glacier? Because I guess if you don't have like a confined channel, then probably stuff just spreads out.
Yeah, we haven't explored that part of parameter space yet with the coupled model, but in Jason's work, in just the melange model itself, it can, he did an experiment for different widths, and it's definitely the case that as the fjord gets wider, the magnitude of backstress goes down significantly. So even with the same linearization, we'd see much less of an impact on the glacier. And for smaller fjords, there's a much thicker melanges and much higher backstress. So certainly that width dependence exists, but I can't quite comment on where it would be.
Say that Justin, who's here, has done previous work on the sort of theory behind what that width dependence should be. So it's a known dependence. Yeah, it goes down.
For one of your last graphs where you showed the newtons per meter, the buttressing strength, Does that agree with some of the thickness measurements from the Meng et al. Paper that basically the thickness is really what's determining the stress and the longitudinal, extensional stress really isn't contributing to it very much? Is that all consistent?
I can certainly give it a closer read, but in my going through it seems to mostly be consistent. And I am seeing that it's mostly the thickness that's driving the determination of the buttressing stress. It's interesting as we explore higher values of alpha, because there are really large changes in calving velocity, and that sort of forces velocity changes within the melange. So there's much greater extension or compression within the melange. So there's, in more extreme values of alpha, it seems like extension's playing more of a role. But I think, to your point, based on observations, that should be a sign that sort of helps us limit what the higher end of alpha should be. For these values of alpha we've been looking at, it is mostly the thickness that's contributing to back stress.
Thank you.
Thank you.
Thanks, Paul.
Thank you.